So this video is a quick short on the overview of chapter 18 and the use of the different equations because we just had an onslaught of a bunch of equations for this chapter. So the very first one that you see right here is your delta S equation, and you can see that it's for the system. For chemistry, we refer to it as delta S for the reaction. And again, this is used when we need to determine whether entropy is increasing or decreasing mathematically. If we can't figure it out from the equation or the process, so for example, if we have a solid producing a gas, you know that it's increasing in entropy. But let's say you have a solid producing a different type of two different solids. That you can't easily determine whether you have a true increase in entropy or not. So you would need to use that delta S of the reaction to determine mathematically whether you have an increase in entropy, which means an increase in disorder or chaos, or a decrease in entropy, which means an increase in order. So that's where you're going to be using that to some extent. Again, the S, the entropy of these products and reactants, is dependent upon phase. So if we have carbon dioxide gas, for which we need to find the entropy, we would go to the appendix in the back of your book to find S naught for carbon dioxide gas. Make sure that you look for phase because it's phase specific. The units for S are also in joules per mole Kelvin. So just keep that in the back of your mind. S units. All right, that's the first equation from the chapter. The second equation dealt with figuring out delta S of the surroundings. Essentially, this morning we learned that delta S in the universe had to be increasing in order for a reaction or process to be spontaneous. And so from that, we found that delta S of the universe was equal to delta S of the system or reaction, which we just talked about, how to determine that, plus delta S of the surroundings. And we haven't yet had a way to find delta S of the surroundings, but now we do. And you can see that it can be based off of the heat of the system. Remember from way back when that heat is found by M times S times delta T with specific heat, or you could find Q from C delta T where we have heat capacity. Delta H of the system can also be found from products minus reactants, very similar to your delta S. You won't use this often, but I did want to include it here to let you know that you can ultimately find delta S of the universe by using delta S of the system from the previous slide, where we had products minus reactants, and then using this delta S of the surroundings. Now it'll depend on whether you use Q or delta H, but again, if you use delta H here, you could do products minus reactants. The next two equations, which you will use quite a bit that we've referred to, are delta G of the reaction. It looks very similar to your delta S because it's also a state function. You'll notice we have delta G not here and delta G not here for our reactants. Again, those come from a table. Remember, the not means at standard temperature and pressure, standard temperature of 25 degrees Celsius and pressure of 1 atmosphere. That's the only time you can use this products minus reactants. But if you are at temperatures other than 25 degrees Celsius, okay, other than 25 degrees Celsius, you have to assume the change in delta H and delta S is negligible. And when you do that, you will use this equation. And it gives a pretty good estimate at temperatures that are not at 25 or 298 Kelvin. Notice you have delta H of the reaction and delta S of the reaction. Temperature here, of course, should be in Kelvin. And again, you will use this delta G when not at 25. You will use the top delta G when you are definitely at 25 degrees Celsius. So for this bottom one, to find delta H of the reaction, again, you have the products minus reactants. The long version, of course, is the sum of the number of moles, so forth. And then, of course, the delta S from the first, where you also have products minus reactants. Again, the long version of that. Next equation, what if you're not at standard conditions? How do we find delta G? Now notice this delta G is very different. We have a delta G naught here. Again, that delta G naught refers to a situation when we are at standard temperature and pressure. But what if we're not at standard temperature and pressure? Then you can use this equation. So that means when you are not at 25 degrees Celsius, again in this equation, the temperature is still in Kelvin, when you are not at 1 atmosphere pressure, and when you are not at 1 molar concentration units. You'll notice here we do have a Q, which is the reaction quotient. We have an R, which is the gas constant, 8.31 joules per mole Kelvin. So for example, this morning in class, we did an example where you had to find delta G of ATP in the muscle. And so again, the muscle in your body is at 37 degrees Celsius. So we would have to find delta G under non-standard conditions for that particular reaction. And you would use this equation. So again, non-standard conditions, not at 25, not at 1 atmosphere, not at 1 molar. Here we have a next equation. It's delta G naught is equal to negative RT ln of K. You'll notice here, though, we've got the delta G naught. That means at standard temperature and pressure. We have R, which is our gas constant again, 8.31 times joule per mole Kelvin. We have K here, or T here, which is again in Kelvin, and natural log of K. Yes, that's right, your equilibrium constant. You will use this when you are at standard conditions, therefore delta G naught, and you need to find K. So for example, you can go from G to K, or you can go from K to delta G. So now we've got a way to go to find a K when we need it, and we don't have data like equilibrium concentrations, for example. And we can also find delta G when we are given a K. So it allows us to go back and forth between the two. Here's the next equation. This is a lab-based equation. So when you do the thermodynamics of the solubility of borax, excuse me, you'll have to calculate delta H and delta S. And through that information, you're going to generate a graph, and you'll notice this is y is equal to mx plus b. So this is for experimental purposes as to when you will use this equation, although you could use it to find delta H and delta S under conditions if you know what the K value and the temperature are, because again, K is dependent upon temperature. So here we have K, and that's going to be determined from your lab. You're going to determine your KSP, and we have 1 over temperature. And so when you do that graph, you have natural log of K versus 1 over temperature, and that's going to be Kelvin to the minus 1, and you'll have a slope. And you'll notice up here that that slope is equal to negative delta H over R. R we know as 8.31 joules per mole Kelvin because we're talking in terms of energy units, so we need to use the energy form of R. And you can find delta H. We also have B as part of our equation, and B is equal to delta S, or the entropy of the reaction, divided by R. And again, that R is our gas constant in the energy units. So from the graph, we can find both delta H and delta S of a reaction. And again, this is generally used for lab-based problems. That's the last equation. Just to recap, here's your lab-based problem. Here is your delta G to K and K to delta G. Here we have our delta G is equal to delta G naught plus RT ln of Q. This is our non-standard conditions, so we can go from delta G and still be able to determine it when we're not at 25 degrees Celsius, for example. And then we have our 2 delta G reactions. One, notice where we have the naught, so we are at standard temperature and pressure. Go to the back of the book and look at those. We have delta G naught also, though, when we are not. So here we are not at 25 degrees Celsius. We can still use delta G equals delta H minus T delta S. You'll notice those knots, but it does give us a pretty good approximation. And then lastly, the delta S naught of the system, products minus reactants, to find out whether the entropy is increasing or decreasing.